Today we are discussing about uh,
Okay. So today his topic of discussion will be biomass gasification with fixed and fluidized bed gasifier. So Gajananji, over to you.
thank you, madam. Thank you very much.
Please start.
So, is my PPT visible to all?
Yes, sir. It is visible.
Okay. So today we are discussing about the biomass gasification with fixed and fluidized bed gasifier. So why we have to go for it? So day by day there is a population is increasing, then atomization is increasing, industrialization is increasing, and there is a scarcity of the fuel. What the prices of the fuel, it's reaching to the rupees 100. So what we have to do? It's time to think. We have to go for the alternatives. Then there are the alternatives, various alternatives: tidal energy, wind energy, solar energy, geothermal energy. So other than solar energy, all are site specific. All energies are site specific. But if you observe that in case of the solar energy, there is still a problem that we could not encash the solar energy, we could not convert it. Then sources will be remain with us, that is the biomass. And a biomass agro waste is in ample amount, in the India, because around 70% peoples are doing the farming. So this agro waste, what it will be? It's just a waste. It will be damaged, or there will be the biological degradation, biodegradation. Okay. So then how we can encash this biomass? How we can convert this biomass into the energy? So it's the major thing. Then biomass gasification, the traditional way we know. In our childhood, we had also seen that in villages, particularly, how the food is preparing. So with the firing of the wood, we are preparing the food, and there will be a lot of energy loss, as well as pollution creation will be there. Pollution. When we are talking about the pollution, all this will be also causing the pollution. But when typically we are talking about the biomass is nearly known as the zero carbon credit fuel. How it is? In first lecture also, Manjula madam has also explained, there is a photosynthesis process. In photosynthesis process, in presence of sunlight and carbon dioxide, the plants are producing the food. So when it is burned, so CO2 will be emitted. At the same time, the energy will be produced. So hence there will be the balance, somewhere there will be the balance of carbon dioxide. Hence it is called the zero carbon credit fuel. Then what will be the applications? If we go for the applications of gasification, so it will be for the power generation, okay, industrial drying. In case of the industries, the producer gas will be used for the drying purposes, steel annealing, spray drying. In case of the boilers, for heat generation, sericulture, and here should be nothing but you are observing, it is a money plant. It is the money plant. So in short, the money plant, we observe many people are keeping in their home the money plant. Okay, it's the good sign. But what's the plant? Plant is giving a money to us in all the ways, in terms of food, in terms of energy. Okay, and then this biomass. I am not always in favor of the jungle cutting. Okay, so that we'll use that biomass, but there is ample of agro waste. Okay, there is a rice husk, there is a soybean husk, wheat husk, okay, moong husk. So all these husks, ultimately it is a wastage. So we have to use this. Then at first we have to learn the gasification process. What mean by gasification process? We know the combustion. Combustion, what is the combustion? Suppose we are taking fuel as a methane. Methane, suppose there is a CH4. CH4 in presence of oxygen, when it burns, it produces CO2 and H2O. There will be the complete combustion. CO2 and H2O plus energy will be produced. So this is we are saying it as a gasification combustion process. This we are saying it as a combustion process. But gasification is what? Gasification is a partial combustion. Gasification is a partial combustion. Means amount of oxygen is less, which is required for the combustion purpose. So gasification processes has the reaction, various reaction. First part is the oxidation reaction. Second part is the reduction reaction. So it is a thermochemical process. It is a thermochemical process. Heat is there, also chemical process is there. So reactions will be there. So reactions are oxidation reaction, C plus O2 gives CO2, and it will liberate 393.8 megajoule per kilomole of energy. Hydrogen is there, H2 plus half O2 gives H2O plus 242 megajoule per kilomole of energy. So this is the oxidation reaction, means combustion is there. Okay, heat is generated, and with the help of that heat, it undergoes the various processes. So at first, what happens? There is a drying process, means what will be the moisture in the biomass that will be removed. When it is dried, so heat will be given, that heat will be utilized for the pyrolysis process. Now what is the pyrolysis process? Now many times you have seen that a matchstick at your home, okay, there is a matchstick. After firing the matchstick, what we observe? There will be the fire at the tip of the matchstick, and after that there is one layer, okay, and at last there will be the unburned carbon, right? So what is that layer? That layer is nothing but it is pyrolyzed oil. At first biomass is converting into the oil. It is called as the pyrolyzed oil. That oil is converted into the gas, okay, and some part of the biomass will be remains as it is. It is the heavy hydrocarbon. It could not be cracked. So then pyrolysis process is there. Okay, drying is a thermal process, means heat is given. Okay, moisture is removed, thermal process. Then next is the pyrolysis process. It is also the thermal process. So a pyrolyzed oil will be produced, gas will be produced. Then next will be the reduction process. So how these processes are occurring? They are absorbing the heat which is in oxidation process. So then next is the reduction process. Reduction process has the various reactions. First one is the Baudgard reaction. CO2 plus C gives 2CO and accepts 176 megajoule per kilomole. Then water gas reaction is there, that C plus H2O gives CO plus H2. It also accepts 131.4 megajoule per kilomole. Then water shift reaction is there, CO2 plus H2 gives CO plus H2O plus 41.2 megajoule per kilomole. So this is the water shift reaction, means CO2 and H2 combining together under certain conditions and producing carbon monoxide. Then methane production reaction, C, that is carbon plus 2O2 gives CH4 plus 75 megajoule per kilomole. These are the reactions. Then how much processes are there in gasification? That is, first one is the oxidation. It produces the heat. Then drying, pyrolysis and reduction process. Here you are observing one figure. There is air. It absorbs the air. Any combustible biomass material produces carbon monoxide, hydrogen, methane, tar is there, and dust. So carbon monoxide, hydrogen and methane, This combination is known as the producer gas. This combination is known as the producer gas. So what is happening here in morning lecture, madam had explained about the biogas. Here we are discussing about the producer gas. What is the difference? Biogas is also known as syngas, but in case of syngas or biogas, 60% methane is there, more than 60% methane is there. In case of producer gas, around 18% there is carbon monoxide, around 16% there is hydrogen, and only 4% is methane. Only 4% is methane. So that is the main difference in producer gas and the biogas. Here the byproduct is also the tar. Tar is the heavy hydrocarbon, which is not cracked. That heavy hydrocarbon is not cracked. It remains as it is, and we'll learn how it is creating the problem. And ash, that is dust, that is the byproduct. So during this gasification process, we have to think about the tar destructions. Just now we have discussed about the tar. Tar is a heavy hydrocarbon, and if we are successful to destruct this heavy hydrocarbon, then also we can produce a gas from it. So there are the various processes: reforming, thermal cracking, steam cracking. Okay, so it gives CO2, COH2, methane. Then steam reforming. Suppose there is a CnHX, it will be at high temperature. At high temperature, a steam will be there. It is reacted with the hydrocarbon. It produces H2 and carbon monoxide. Then here you are observing dry reforming, the another process. Dry reforming is again a hydrocarbon is reacting with carbon monoxide. It produces H2 and carbon monoxide. So in case of thermal cracking, high temperature, tar is heated at high temperature at around 1100 degrees Celsius. It is cracked. It is cracked into carbon monoxide and the hydrogen. Steam cracking, tar is dilated with steam, is briefly heated in furnace in the absence of oxygen. In the absence of oxygen. Researchers, what they are studied, pyrolysis process is a mechanical process. It is occurring only due to the heating in absence of oxygen. Okay. So similarly, steam cracking you are observing here also there is no oxygen. In presence of steam at high temperature, it is cracked. Tar is cracked. What is tar? That we'll learn afterward. Then come to the main point. We are starting a gasifier. The device in which the gasification process is going on, that is called as the gasifier. Then there are the two types. Major types are fixed bed and fluidized bed. Fixed bed means what? What will be the fuel inside it? What will be the fuel inside it? That is in batch we are providing it. Means suppose a container is there. So we are feeding in it a biomass. Suppose it around 30 kg, 40 kg, maybe up to 100 kg as per the capacity of the gasifier. It will be sealed. Okay, it will be sealed with the surrounding. So there will be no interaction in between now container and surrounding. So hence now the mass of the biomass is fixed. What we have to gasify, that mass is fixed. So it is called as the fixed bed gasifier. Then fixed bed gasifiers, there are various types of the fixed bed gasifiers. Updraft gasifier, cross draft gasifier, and downdraft gasifier. As here you are observing in this figure, name is indicated updraft gasifier. What is this updraft gasifier? What you are observing here, air is entering from the bottom side, and gas is coming out from the top side. Okay, so here there is oxidation process. Oxidation process is at the bottom. Oxidation process is at the bottom, and this heat is transferring towards the top side. So what will be the biomass? Though here don't consider figure as it is, because it is the random process. It is the random process. Okay, so we could not categorize it into some layers. Just for the understanding, these figures are prepared. So oxidation, a combustion will be there, heat is produced, that heat is moving towards the top side. So at the top there will be the drying. Next layer is the pyrolysis and reduction. That is the chemical process. Reduction reaction is there. Here carbon monoxide and hydrogen will be generated and the gas is produced. From top side biomass is fed. So how the gas production, how the flow is from bottom to the top. Flow is from the bottom to the top. Then second case you can observe, that is the cross draft gasifier. That is the cross draft gasifier. In cross draft gasifier, what you are observing? It is entertained flow. So air is coming on one side. There itself, there is a combustion. As the combustion is going on, what will be there? It is coming down and producer gas is taken out from the another side. So biomass is entering from the top. After batch feeding, it will be completely sealed. This biomass is sealed. Okay, this will be sealed. This will be sealed, right? So this is cross draft. On one side coming, on another side it is going out. Then there is a downdraft gasifier. Downdraft gasifier. What the downdraft gasifier? Updraft. Gas is taking from the upside. Downdraft. Gas is taking from the downside. Downside in comparison with the entrance of the air. How the from where air is entering. From where air is entering. Okay. So what you are observing here, air is entered here. There is a combustion process. Here is combustion is going on. Okay. Combustion heat will be again going towards the top side. Top layer will be dried. In between, then there will be the pyrolysis. And what is the next? What is the difference? Difference is that here reduction process is downward. Okay. Here reduction is going on, and this reduction produces the producer gas. Okay. And as the flow is downflow, flow of the producer gas is downward side. So it is obtained from downward side. So it is called as the downdraft gasifier. Then next is the fluidized bed gasifier. One thing you learned that what is the fixed bed gasifier? Fixed bed gasifier means we are providing the feedstock in batches. Okay. What is fluidized bed gasifier? Here feedstock is fluidized. Now what mean by fluidization? Here the question will come in mind that there is a solid, biomass is a solid. Okay. And how we are saying that it is fluidized? Means what mean by fluidized then? What mean by fluidized? So how can be the solid work as a fluidizing material? So what is the property of the fluidization? So fluidized, some again thing will be come in mind. There will be the liquid. Okay, it behaves like a liquid, so it is fluidized. Okay, but not now. You can see this bottle. In this bottle there is a water. Just I will explain this with another figure. I can explain. We know, suppose we are taking a glass of water. And this is the glass of water. It contains the water. Okay. So this contains the water. So what happened? Suppose you are tilted this glass in this way. Okay, now this glass is tilted. So what about the water? Water will be in this position. Water will be also in this position? Yes. Yes? No, not at all. Am I audible? Am I audible?
Yes, sir, you're audible.
Yes,
It
sir.
will not be tilted.
So this water will be, is the layer will be inclined position? How, what will be your observation? Have you tried sometimes? Okay, second example, in morning you are taking a tea. In morning you are taking a tea. In a cup, when the cup is kept on the table, at that time, what will be the level of the tea in the cup? Now you want to take that tea, so at that time you are tilting the cup, tilting the cup. Then what is your observation? Is that layer also tilted? Never. This layer will be always horizontal. This layer will be always horizontal. Okay. Though it is tilted, but water, that fluid will be always maintain the horizontal layer. Fluid always maintain the horizontal layer. And if any solid possesses this property of the fluid, okay, that is called as the fluidized material. That is called as the fluidized material. Then a sand is there. Okay, have you observed the sand? So you are taking sand in a cup, just observe what happens. If you tilt the sand, if you tilt the glass, what happens? That sand also takes the horizontal position. So such kind of the material is used for the fluidization purpose. Such kind of the material is used for the fluidization purpose, and that is the where this occurs. So using the principle of solid material, using this fluidized property of the solid material, we are obtaining the fluidization process. Then what will be that? Here you are observing the figure. This is the figure. In this figure, a aerator will be there. So steam or air will be entering. Here there is a mesh of the small holes. Mesh of the small holes. And this mesh, above this mesh, from this there as around 1.5 mm, 1 mm to 1.5 mm, sometimes 1.8 mm holes are made on this. So through this air is passed. So this air, here a bed of sand will be there. Bed of sand. Now above this sand we are pouring the biomass. Above this sand we are putting the biomass. Okay. So what happens when this air is aerating? When air is aerating or coming at pressure, okay, inside it, so that sand will be just behaves like a fluid. So just you are observed the bubbling. If you are passing air through the water, there will be the bubbling. The same pattern will be followed here. And what is happening then? This sand carries biomass with it. This sand carrying the biomass with it. That is the fluidization process occurring with the sand for the biomass. Then here there will be some heating element is provided. Either you are using steam, then no need of the heating element. Okay, steam itself has a temperature around 700 degrees Celsius, 800 degrees Celsius. And how much temperature will be required for the gasification? It around 400, 500 degrees Celsius is enough temperature for the gasification. We learn that afterward. So here, then the biomass is coming in contact. Again, it is converting. The same processes will be there as we learned in case of the fixed bed gasification. A gas will be formed. That then biomass. This is particularly the example of circulating fluidized bed gasifier. So here is the cyclone. You are observing the cyclone. What is this cyclone? Cyclone separator. You may heard the name. Okay. So how it will be? Cyclone separator. So figure is in this fashion, right? Figure is in this fashion. Okay. So gas is coming from this side. So this gas is coming and it is moving like this. Okay. What will be the material? So here there will be the centrifugal force. Here centrifugal force. Due to this centrifugal force, what will be? It will be separates solid and gas. This will be separating solid. This is the solid and the gas. So what about the gas? Gas is the light. So it is coming from the top side. So gas is coming from the top side. What will be the earthward product? Because when it is coming from the fluidized gate gasifier, not only the gas is coming, because this is aerator, air is coming from the air, aeration is going on, and sometimes it will be by the centrifugal pump, or sometimes it will be by the it will be by the compressor or centrifugal. Okay, so here air is coming with along with the unburned hydrocarbons, so that solid particles is coming downward and it is again provided to the gasifier unit. So this is circulating. This is circulating. Hence it is called as the circulating bed gasifier. So gas is coming from the top side. Gas is coming from the top side. Here you are observing this is the cyclone. Under centrifugal force, this solid biomass is returning again. Okay, and this producer gas is coming from the top side. Okay, then there are some case studies. Here you are observing the downdraft gasifier. So here in gasification process, after the gasification, there is a cleaning system. It will be cleaning system. Here in this figure you are observing, there are this is the cleaning system. Various filtration units are used. Producer gas produced from the downdraft gasifier is passed through these filters, and afterward it will be given to the engine. So though there is a gas cleanup system, the producer gas consists of sticky tar. Here you are observing this is the tar. We already discussed about the tar. What is the tar? It is a heavy hydrocarbon. Heavy hydrocarbon means it could not break easily at a low temperature. We have to go for thermal cracking up to the 1100 degrees Celsius. So this is how its nature. It is not only with heavy hydrocarbons but also sticky in nature. So this was, we had visited with the kindness of Honorable Mahanta sir. I have got opportunity to visit this plant, and at that time there was a Ramakrishna Go owner. He was a literally frustrated person. Why? Because this tar was the main headache for him. So due to this, there is a reciprocation between piston and cylinder. So along with the producer gas, so this producer gas is used in either in gas engine or in the dual fuel engine. Means diesel will be there, and through inlet we are providing along with air we are providing the gas. So this gas carries the tar. And as it is in sticky nature, so there will be after some times there will be the clogging in between the piston and cylinder. After some time there will be the clogging of piston and cylinder, and this will be literally stops engine to work. And this is the main headache. Because maintenance, it is the tedious maintenance. It requires time to time. So attempt has to be made to how we can remove this tar from the producer gas. So there is a need of time to search the more efficient technology for this gas cleaning system. Okay, this is another unit, another case study. This is Mesh Synergy Jogigopa. This was in Assam. This was in Durgapur. With the help of the CML, we had visited to this plant. This is another plant in Jogigopa. So they are producing charcoal from the bamboo plant. Its capacity is 100 tons. This is the coke plant with they are producing at actual 70 to 75 tons. So what is observed in this case? Ample of tar was produced. This tar and liquor is separated from the hot gas with cyclone separators. It is separated. Tar is separated from the liquid by natural sedimentation process. And here you are observing this is the unit. Okay, here it will be separated. But ample of tar, what to do with this tar? Okay, coal is formed. Okay, bamboo charcoal is formed. Right. After that, what about this tar? Liquor can be also used in various chemical industries. But what about the tar? So this tar is used for the road preparation, but it is a heavy hydrocarbon. It is a heavy hydrocarbon. If we are succeed to crack this tar, again a gas will be produced, and again we can have a more power generation through this tar. So this is the dual fuel engine you are observing. Okay, so producer gas is given to the dual fuel engine. It produces the power. Okay, but main headache we had discussed for this. Okay, so this is the engine running on producer gas. This is the engine running on producer gas. So then when we are studying about all this, we have to go for the characterization. We have to go at first for the characterization of the biomass. So though we are going for the experimentation with the fixed bed gasifier and with the fluidized bed gasifier, we have to go for the characterization. Difference is fluidized and fixed bed we have studied, but again, what about the feedstock? Feedstock for the downdraft gasifier or fixed bed gasifiers is required in solid form, where feedstock in case of the fluidized bed gasifier is the fluffy mass. Okay, it is just like a dust, sawdust. Okay, sawdust. Then rice husk. Okay, in powder form. That is used in fluidized bed gasifier, because it is not easy to fluidize the solid materials and to pour the solid materials also inside the fluidized bed gasifier. But same is not possible if we use the fluffy mass. In case of the downdraft gasifier, just it will be dumped, just it will be packed, and there will be no chances for the gasification. Hence, these are the main limitations of both the fixed bed gasifier and fluidized bed gasifier. Whatsoever what we are using the fixed bed or fluidized bed gasifier, we have to go for the characterization of the biomass. So first then, how to know? Because various biomasses are there. It may be the rice husk, it may be the soybean, it may be the wheat husk, okay, which is formed during the agriculture. Okay, it is agro-waste, but we have to do the characterization. We have to come to know what will be its content, what will be its carbon, what will be its hydrogen. Then we have to go for the ultimate analysis. This ultimate analysis gives the carbon percentage, hydrogen percentage, nitrogen percentage, sulfur, ash, and oxygen. So this is a particular example. Sawdust will be 44.547. Carbon, it contains carbon. Hydrogen, it contains 8.872%. Nitrogen 4.462. There is a no sulfur. There is a ash only 1, and oxygen will be 41.119. Similarly, you are observing for the rice husk composition. Similarly, you are observing for the mustard husk powder. You can go for the soybean or any other agro-waste also. And it is a beauty of I am saying beauty of the biomass, that it has a very less sulfur content, which avoids about the acid rain. So nowadays co-gasification, where the researchers are going for the co-gasification. What mean by co-gasification? Combination of coal and biomass. So this will be mixed in certain proportion. So what will be benefit? Sulfur dioxide. What will be sulfur dioxide forming in case of the coal? That will be reduced by using the biomass with it. So this is the ultimate analysis, characterization. So how we are producing, how we can produce fixed bed, feedstock for fixed bed. So in general, there is a normal process. We are taking the wood. There is a wood cutter you are observing. With the wood cutter, we are going for the wood chips. But is it desirable to use these wood chips? No, because we have to go for the jungle cutting. Okay, we have to go for the forest cutting. So we have to avoid this. Then what will be the alternative methodology? Alternative methodology will be prepare the briquettes. So how the briquette? We had set up one example under the guidance of my sir. So he suggested to use a binder as a best newspaper at that time. What the role of best newspaper? Had you observed sometimes if you put the newspaper in water, so it produces somewhat sticky liquid. So we had used in proportion this waste newspaper, biomass, water, and by hand. These are the briquettes formed by the hands. These are the briquettes formed by the hands. Then this sticky solution of water newspaper and water, okay, water newspaper, waste newspapers and water, plus sawdust, maybe rice dust, maybe mustard dust. So manually we had formed the briquette. We had used the various compositions. So type of material, we had nominated it as a B05. B05 means what? Biomass 95%, waste newspaper as a binder 5%, B10, B15, B20, B25. So we had observed that a B25 is there, then you can use this briquette as a ball for playing a cricket for a small while. Okay, so that much strength it has. That much strength it has. Next is what we can produce the pellet. Here you are observing the pelletizer. Here you are observing the pelletizer, and in this pelletizer, so there is a rollers. Okay, these rollers, and here is a holes through which a biomass will be compressed in between rollers, and this roller is rotating, as well as it is rotating about itself as well as about the lock nut also. Okay, so that biomass will be compressed in between it, and a pellet will be obtained. Pellet will be obtained through it. Then at that time, we work on dolomite can be a good tar cracker. So to reduce the tar, we had used the dolomite. And mixing this dolomite, we had checked with the X-ray diffraction pattern the properties of the dolomite also. Okay, so it is as per requirement. So this is the X-ray diffraction pattern you are observing. So this will be obtained, and we use this dolomite. Okay, and pellets will be obtained. So high pressure, there will be the high pressure as well as a heat. Due to rotation, there will be the heat also, and pellets will be formed. So pellets composition again, biomass and catalyst. So P00 we had seeing as a 100% biomass, P10 10% as a dolomite, P20 20% as a dolomite, and like that we had given the nomenclature. So these briquettes, pellets, we can produce from the agro waste. Instead of cutting the wood. Then we had gone for the various tests. First test was proximate analysis. So ultimate analysis that we had seen, ultimate analysis will be done in the laboratory, but proximate analysis we can do in a muffle furnace. Okay, in a muffle furnace. What will be the condition if we keep at around 100 degrees Celsius, 105 degrees Celsius in a muffle furnace for 3 hours? Whole moisture will be removed. Okay, so you will get a completely dry briquette or pellet. Then volatile matter, how can we obtain the volatile matter? So 550 degrees Celsius. So this is the with in absence of air, or that we have to do just the heating process. 9 minutes, only for 9 minutes we have to heat it, and what will be the difference of weight? That will be the volatile matter. So then we have to heat it at 550 degrees Celsius for 6 hours. So it will be completely burned and ash will be remain. Then how much is the fixed carbon? Fixed carbon equal to this is considered total as 100 minus moisture content plus volatile matter plus ash, that is the fixed carbon. Okay, so this will be the total solid. So what we are obtaining, how much is the moisture, how much is the volatile matter of that biomass, okay, how much is the fixed carbon of that biomass. Okay, then here you are observing the another figure. Here we are checking the hardness of this briquette and pellet. okay, briquette and pellet. So it is found that it is suitable because for transportation purpose, if we are transporting briquette and pellet from one place to another place, it has to restrain. It has to restrain, and that will be checked by this hardness tester. Then here you can observe these are the properties. So moisture content, okay, in weight percentage. So sawdust, rice husk powder, mustard dust powder, briquette. For sawdust, there will be the more moisture content, where for the mustard dust it is observed that it is less. Okay, volatile matter will be the same situation. In case of ash content for the sawdust is more. Ash content for the sawdust is more, and somewhat more than that there will be the mustard dust. But for the rice husk, there will be the less. There will be the higher ash content by weight. Higher ash content by weight. Where here you are observing the fixed carbon. Fixed carbon is observed more in case of mustard husk. Fixed carbon is observed more in case of mustard husk, where it will be less in case of the rice husk and the sawdust. Then similarly, same graph we are obtaining for the pellet. Okay, pellet compositions. So sawdust, dolomite pellet, and mustard dust powder. Moisture content, volatile matter, ash, and fixed carbon. Okay, so what you are observing? Sawdust has more moisture. Sawdust has also more volatile matter. Ash content of the sawdust is less. Also, fixed carbon for the sawdust is less. Then impact resistance index. Impact resistance index, how we had calculated? Impact resistance index means you have to just stand on the table and throw the what will be the briquette or pellet to the concrete ground. After how much times it will be break or crack or crash, that we have to count, and then we have to obtain from that impact resistance index. So impact resistance index of here you are observing for the sawdust is moderate. For the mustard husk it is less. Okay. For rice husk we could not say, sometimes it will be fails, sometimes it has a good impact resistance index. Okay. So then density, you know, we had how we are measuring the density. Weight per unit volume. So specified we had taken the just area at random area, volume we had considered, and that weight. So that density we had calculated. Stress we had calculated with the machine. Okay. So you are observing that more, it will be more good. Just rice husk will be there. Okay. This is the rice husk will be there. But for case of the mustard husk, it will be less. It will be less. Calorific value is calculated in bomb calorimeter. So calorific value for sawdust is higher compared to the mustard husk and rice husk. Okay. So ultimately we are observing the sawdust is the good, but it doesn't mean that we have to not go for the other agro waste. We have to find what will be the good agro waste, and we have to go. Though this will be there, this will be the difference, but all the agro waste are giving the producer gas. So for the pellets also we have taken the calorific value. It is observed that all the cases sawdust is good. Okay. Then thermal analyzer is there. Parkinson Elmer's simultaneous thermal analyzer ST8000 thermogravimetric analysis. So it is working on the inert gas. Heat flow rate is used 10 degrees Celsius, and it is heated in between temperature 40 to 900 degrees Celsius. Thermogravimetric analysis. Device is Perkin-Elmer simultaneous thermal analyzer ST8000. So we had gone for the thermal gravimetric analysis. What we obtain? So what we obtain, if we heat a biomass, how its weight is decreasing, how its weight is decreasing. Okay, so as the moisture will be removed from it, so its weight will be decreased. And what will be the heat release pattern at the same time? What will be the heat release pattern? Because when fire is taking place, when the substance reaches to its self-ignition temperature, at that time only fire is taking place. At that time only the fire is taking place. So here also means a heat liberation will be started. Here also we are studying that. Another you are observing Vansoet method, Pelican Mech fibrous plus analyzer. So here we are finding the characteristic lignocellulose characteristic, cellulose, hemicellulose. These three components in it. Okay, so reflux heater is there. Samples are placed in the crucible. Okay, and it will be just fluidized at certain temperature. So you are obtaining its contents. Okay, so thermogravimetric analysis you are observing here. Again, we have done for the sawdust. Okay, rice husk, mustard husk. Sawdust, rice husk, mustard husk. What you are observing? There are the 4 phases. Okay, so temperature, in between temperature 100 to 200. As such, so from 200 onwards it is starting to decrease. Okay, it is starting to decrease its weight. Okay, so weight will be decreased drastically. Okay, and afterward then there will be the graph is moving upward. Okay, so up to this, so this is the main phase. This is the main phase. Here it undergoes pyrolysis, it undergoes the reduction process, and gas will be obtained. Okay, so this is the again same figures are there. Now come to the experimental setup and what will be the procedure if we want to perform an experimentation on the downdraft gasifier. Okay, particularly specifically we have selected the downdraft gasifier because in case of the downdraft gasifier, as you had observed this figure, you are observing this figure, what is at the top? Drying. After all, what is it? Pyrolysis. And what will be hold this biomass is coming through the combustion process. Okay, so it will be undergo the combustion, means high temperature will be there. So what will be the inline tar cracking? This is we are saying as an inline tar cracking is more desirable in case of the downdraft gasifier. Hence, we are selected for the experimentation downdraft gasifier. What you are observing here, a biomass will be fed from the top. This is the vibrator. Vibrator means it is slightly vibrating to the gasifier. Why? Because there is a possibility, though there will be the pellets, briquettes, or maybe the wood chips. It will be just packed. Okay, so it has to be moved somewhat so that it will be go downward. These are the 2 pipes, air pipes, through which air is entering into it. So this unit you are observing. Okay, here this is the hopper is the separate unit. Reduction chamber is the separate unit. Ash chamber is the separate unit. In reduction chamber, there is a gasification process. Okay, in presence of carbon. Carbon, how? Here we are providing a light charcoal bed. Okay, light charcoal bed. So what will be here? The coke is coming downward and heat will be there. So it will be undergoes a gasification process. Then first what is done? First care is what? First treatment is given to the gas. And what kind of the treatment? A water, it will be cooled by water. Okay, you can say it is a direct type heat exchanger. Direct means what? Gas and water are mixed with each other. Gas and water are mixed with each other. What is happening due to that? So at atmospheric temperature, tar is solidifying. Otherwise, it will be in the vapor form. So what is done here? When it is bringing in presence of the water, it will be get condensed. Okay, and due to that it is coming downward. Then it is passed through the coarse filter. Coarse filter means what? Just it is a filter in which biomass will be kept. Okay, husk will be kept or powder will be kept. Through that a biomass is passed. Next is the fine filter. Fine filter means a cotton bag is there. Through that cotton bag, a gas will be passed. So at each and every step, we are trying to that how the tar will be get separated. Tar should not go inside the engine because it is creating headache. It is creating headache as it is sticky in nature and heavy hydrocarbon. So as it is heavy hydrocarbon, it could not break, and at its sticky nature, what will be the reciprocation? That will be deleterious. So then this gas, what will be the gas obtained? That gas is then passed through the engine. It will be given to the engine. Engine is connected to the generator and power will be produced. So here we are taking the gas for the gas chromatography sample to measure its contents. Okay, so here you are obtaining the flare. Okay, flare of the producer gas. Then this water will be given to the underground. What will be the tar that will be collected? Okay. Then this is the actual setup you can observe. This is the actual setup. It is available in IIT Guwahati in energy lab. So here you are observing. This is the air. Okay, we are passing the air through these pipes. This is the air flow meter. Air flow meter provides the flow rate. Okay, air is supplied to the air flow meter, and from it on two sides there is air inlet. Okay, this is the hopper. This is the hopper. Okay, so thermal analysis we had carried out for this. Thermal analysis means we want to know what temperature is there and how the gasification process is taking place. At what place, what temperature will be there, and how the gasification process is taking place. So for that, here you are observing the thermocouples. Thermocouples are there. Okay. So then this is the engine. Okay, dual fuel engine. This dual fuel engine is using diesel and a producer gas. This is the data acquisition system. Data acquisition system gives the very minute readings. Okay, very minute. In microseconds, it is giving the readings. What temperature will be there? Lower part you are observing. This is the reduction chamber, and here is there is a scrubbing unit. Scrubbing unit means water and gas will be directly exchanging the heat. Tar in gas will be condensed, and then it goes afterward to the filtration unit, and tar will be accumulated in one tank. Okay, so how the thermal analysis is carried out? So thermal analysis, here we had put the thermocouples T1, T2, T3, T4 at the different circumference you are observing at various circumference. So basically the gasification process, or you can say the combustion process, is the random process. We could not separate it into the zones, but for our understanding, we had made the various zones: drying zone, pre-pyrolysis zone, pyrolysis zone, pre-combustion zone, combustion zone, reduction zone. Okay, and there is an ash chamber. So here at various locations we had calculated the temperature. We had seen the temperature. So what temperature will be there? How the process is going on inside? And then in reduction chamber also we put the thermocouples. Means the reduction process at what temperature is taking place. At what temperature it is taking place. So this is, you are observing how the thermocouples we had poured inside it. These are the holes. So thermocouples, these are thermocouples. So this is the thermocouple casings. We had taken the pipe. So through that thermocouple we had passed, and that thermocouple is sensing the temperature and gives the temperature. Okay. So how much temperatures are used that are given here. Inside the gasifiers there are 18 thermocouples. In producer gas line there are 7, and a surface of the gasifier there are the 11 thermocouples. Surface we had put the thermocouples means how much heat is also going to the surrounding, because you know heat is transferring by conduction, convection and radiation. So how the heat is transferred to the atmosphere and how much it will be. So for that also we had kept thermocouples at the surface. Okay. Then this unit you are observing in detail. Okay, detail. So this is the scrubbing unit. Here this is the scrubbing unit. Okay, this is the tank where the tar will be collected. Okay, here you are observing this is the collection chamber, small. Okay, then this is the tank. Okay, water will be circulated, right? So these are the filtration unit. This is the filtration unit. Then afterward, gas flow rate also we are calculating how much gas is obtained, how much air is supplied, how much gas is obtained. Okay, and this is the flame you are observing. This continuous flame we are getting. Okay, this continuous flame we are getting, right? So this is the blue flame you are observing. This is the red flame. When red flame or yellowish flame will be there, when there will be some light water content will be there, at that time it behaves like this. So here flame we are getting, we generate the producer gas, okay, in the lab at IIT Guwahati, and this will be utilized in the dual fuel engine, okay, which is connected to the generator. This unit is connected to the generator, which produces the electricity, So here you are observing, this is the filter 1, okay. This is the tank. Here you can observe how much tar is collected, okay, how much tar is collected, water tank, okay. So then this is the coarse filter. Coarse filter means biomass, okay. Here the sawdust is kept, through it a gas is passed. So here the tar is accumulated. This is the fine filter. A cotton bag is there. Through this a gas is passed. So a tar will be collected here. Okay. So in this way, the gas cleaning unit is taking care for the gas cleanup. Then experimental matrix. Now you observe that, you just listen that at the first we had gone for the ultimate analysis. From that ultimate analysis, we had find carbon, hydrogen, okay, carbon, hydrogen, nitrogen, and all that. Then from that we have to go for the formulation. Okay, there is a way for the formulation. We have not enough time for the formulation of the biomass. We have to go for the formulation of the biomass. Then we have to calculate the equivalence ratio. Okay, equivalence ratio. How much air is there? How much air is required? Okay, so that equivalence ratio is there, 0.19, 0.21, 0.29. Because air flow rate, how much air we are providing, that we had measured. How much producer gas is there, that also we had measured. Okay, so this will be gives the equivalence ratio, and that gives us the thermal behavior, gas chromatography, and tar evaluation. That will be the findings we had done. Okay, for all that, mustard dust we had titrated at 0.32 equivalence ratio, sawdust with dolomite pellet at 0.32. Okay, then this will be the thermal analysis. Okay, how it will be behaving in drying zone. So at initially it is at 30 degrees Celsius at around atmospheric temperature. Then this temperature is increasing. Okay, it goes up to the 85 degrees Celsius. Okay, then pre-pyrolysis zone, it goes up to 200 degrees Celsius. Then in pyrolysis zone, how much temperature is there? Up to 250. Okay, in pre-combustion it is up to 450. Then in combustion you can observe, this is the combustion. So 1000 to 1200 degrees Celsius, the combustion process is going on. Ash chamber, that will be hot. Ash is hot, so sometimes it goes to the 85 degrees Celsius. So in various zones, if we observe, these are the various zones, thermal analysis is carried out. So it is at most, it is in combustion chamber. Okay, combustion chamber. Then there will be the reduction zone. Okay, reduction is taking place at 450 degrees Celsius. Means gasification is taking place at 450 degrees Celsius. Then the drying and all that will be at the low temperatures in between 0 to 200 degrees Celsius. Similar profile will be carried out. Okay, so for the wood chips, okay, with equivalence ratio, these are the temperatures, right? Then suppose we are considering this is the gasifier. Okay, so this is the drying zone. How much will be the temperature here? Just it goes up to 85 degrees Celsius. Here from this graph, you can come to know that how much temperature. In pre-pyrolysis, temperature will be around 100 to 120 degrees Celsius. In pyrolysis, it goes to 180 degrees Celsius. Here in combustion zone, temperature is at around 1000 degrees Celsius. And then there will be the reduction. reduction will be at around 350 to 400 degrees Celsius. 350 to 400 degrees Celsius. Okay, and then there will be the, at last there will be the ash will be 50 to 60 degrees Celsius temperature. So this is the gasifier, and at how much height, what kind of the zone will be there. So drying zone, we just for understanding purpose, drying zone, pre-pyrolysis zone, pyrolysis zone, pre-combustion zone, combustion zone, and reduction zone will be there. So in that way, and we have obtained this thermal analysis. So we can get it that combustion process is going up to 1200 degrees Celsius. That much temperature is required. At the same time, reduction means gasification process can be obtained just at a 400 degrees Celsius. So this is for the wood chip. Okay, this is. Then what will be the gas composition obtained from the gasification of various feedstock with different equivalence ratio? Don't go that much details of the equivalence ratio. Just see composition. Hydrogen is how much? 16.87. Carbon monoxide 17.04. Methane is 2.18. CO2 is 14.12. Nitrogen is 49.35. Okay, in this way. So these are the equivalence ratio. At various equivalence ratio, experiment is carried out, and how much will be the gas composition? We are collecting this gas into the Tedler bag, and we are going for the gas chromatography afterward. So that will be gives the gas composition: hydrogen, carbon monoxide, methane, CO2, and N2. Similarly, for sawdust pellet, P20 was the good composition, giving hydrogen 17.9, carbon monoxide 22.8%, methane 2.67%. Okay, and gas flow rate is also 2.41 Newton meter cube per kg, normal meter cube per kg. Okay, so comparative analysis: sawdust dolomite pellet P20 give the good composition of the producer gas 17.90 hydrogen, carbon monoxide is 22.80%, methane is 2.67, carbon dioxide is 16.39, and N2 is 14.1. We are interested in this only: hydrogen, carbon monoxide, and methane. Hydrogen, carbon monoxide, and methane. How much it is? Then tar collected. So this is the water tub. How much? Water tank, coarse filter, fine filter. So 4.354. Okay, 4.354 grams. If we are going for the continuous, then it will be collected in higher amount. Okay, where it is collected less, that we have to find. So here it is only 2.080. 2.080. This is gram. Okay, this will be gram. Okay, 2.080. Then similarly it will be for the producer gas flow rate. How much it is? Calorific value of the producer gas conversion efficiency, how much biomass is converted into the gas, how much carbon conversion efficiency, that we had calculated here. Here you are observing. So suppose there will be the 0.29 equivalence ratio, then 2.26, calorific value 5.19, gas conversion efficiency 65% it is converted, carbon conversion 90% it is converted, 90% carbon is converted. Okay, then we have to go for the tar cracking. Okay, we are moving towards the end now. So tar cracking, we had already seen reforming, thermal cracking, and steam cracking. Okay, I will not discuss again in detail. We will go for the experimentation. Then bubbling fluidized gasifier. Bubbling fluidized bed gasifier means in which the substance will be fluidized. Substance will be fluidized. So what we had done here? Here a tar we had taken. Okay, it operates on principle of bubbling fluidized bed. Various types of the fluidized bed gasifier also. So we have not that much time to go into the detail. It operates on the principle of bubbling fluidized bed. If tar is heated to temperature 800 degrees Celsius that we have seen, it will be cracked 800 to 11 degrees Celsius, thermal cracking. Okay, here also we are using the dolomite as a catalyst. Okay, and it will be get cracked in lower hydrocarbons. So operating matrix is that we are giving heat input through the heater up to 3.5 kilowatt. Air flow rate is 0.15 liter per second. Dolomite weight percentage we are using. Okay. Then water flow rate in gas scrubbing unit, because in a similar way here also we had scrub the producer gas, okay, with the help of the water. So here you are observing, this is the, here we are heating element is there, the tar will be kept here, this is the aeration pipe, bubbling will be done, heat it at higher heat, there will be the cracking of the tar. What will be the result? You can observe this result. Okay, so after 5 minutes, it starts to generate the gas. After 10 minutes, this will be the position. After 15 minutes, it catches the fire. After 20 minutes, this will be the fire. Oh, and after 25 minutes, what will be the rate? Okay, so this will be the gasification. And then as per, because we have done it in that batch process, as the tar will be consumed, so flame will be decreasing and decreasing. And after 45 minutes, so we had carried out this experiment for 45 minutes. You are observing this. Okay. So this is some part aeration pipe we had used, heating element. Okay. This is the air inlet. This is the thermocouples. Also we had gone for the thermocouple thermal analysis. Okay. Elemental heater we had used. Right. This is the air inlet. Okay. Gas outlet. What air is coming, that also we had measured. What gas is going, that also we had measured. Here we had variation of the heat input. Okay, though it is 3.5 kilowatt, but we had started from 5 kilowatt and we had gone for the reaction. So thermocouples are used, and this is the Agilent make data acquisition system through which we had gone for the thermal analysis. So here you are observing the rise in the bed height of the tar for various airflow rate. So it will be at most, this will be the reading. Okay, so weight of the tar, that is 6 kg. At that time, the rise in the bed height was 250 mm. Okay, so in this was the in-house product. This was the in-house product. In the workshop of the IIT Guwahati itself, we had manufactured this. Okay. So what we use, tar dolomite. So tar dolomite blends we had formed various, and we had gone for the various airflow rate, various heat input. Okay. Then thermal behavior we had checked. So it goes maximum temperature heat input at 3 kilowatt, it will be 600 degrees Celsius. At 2 kilowatt, it will be 2.5 kilowatt, like that. Okay. So this is the thermal analysis, just the gross thermal analysis. Then gas composition. Gas composition, here you are observing, it will be better at heat input 3.5 kilowatt. A simple question can be asked, why it is? Because at 3.5 kilowatt, more temperature will be generated, and hence tar will be cracked. More tar will be cracked. It is converting into the producer gas. Hydrogen 9.6%, carbon monoxide 18.6. Okay, that is, and methane will be 2.5. So volumetric cracked gas flow rate residue for various heat input will be 0.0015. Weight of tar 6. So gas flow rate. Okay. Then this is the thermal profile in general. Okay. So this will be the combustion. Here will be the large amount of heat is given, that will be at around 1000 degrees Celsius, and accordingly, so up to the top, it will be reaches up to the just 250 degrees Celsius. So this is the composition, gas composition. So which one is the better? That is tar dolomite. Dolomite with 15% is the good composition. Hydrogen we are getting 16%, carbon dioxide 17, nitrogen 28.5, methane 1.2, and carbon monoxide 37.3. Here with a dolomite percentage 10%, we are getting carbon monoxide 40%, but the hydrogen will be slightly, it is decreased up to the 13.7. Okay, so this is about the some test we had done. Okay, some test we had done. After this, recently we had gone for the another gasification unit. So in my student is there, Professor Tushar Patil. He is doing PhD on development of 3.0 kilowatt power generation unit. Okay, for power generation from agro waste with fluidized bed gasifier. So we are developing a gasifier unit. Gasifier unit we have developed. So this unit will be there. You are observing this. Initially, 2 phases we had gone. This is the 2-year study. In first phase, what we had done, here you are observing, this is a type of the circulating fluidized bed gasifier. Circulating fluidized bed gasifier. Here also you are observing this is the cyclone separator, and unbound particle is coming downward. So this is the feeder. This is the feeder. So feeder, we are feeding the biomass from this. Okay, biomass is coming here. This is the heating element. We had placed the heating element here. So biomass is coming here. Okay, this is the biomass. So what's the problem? So this unit is unsuccessful. Okay, this unit is unsuccessful. This is the unit, actual unit you are observing. So air is coming from the downward. Air is coming from the downward, and as air is coming from the downward, so that is creating back pressure to the biomass feed. Back pressure to the biomass feed, and that biomass is, instead of going to the riser, it is coming out from the feeder. So that was the major drawback. We had constructed this unit and we unsuccessful in that. But in next year, this was the limitation: biomass coming from the feeder in not properly intercirculated into the combustion chamber because of backflow of biomass due to high compressed air flow through compressor. System does not produce sufficient amount of producer gas due to the drawback in design. Okay, then what we done? We removed that. Same unit. This is the same unit. Same unit. What we had done? We had removed the feeder, and instead of that feeder, there is a screw feeder. Major modification. We had added a screw feeder in this. This screw feeder. Now we are feeding this biomass with this screw feeder, and this is the successful unit. We are capable to generate the producer gas. Here you are observing a producer gas is generated with this. These are the some glimpse. The producer gas is generated with this fluidized bed gasifier. Okay, here through the screw feeder, we are providing the biomass. We are feeding the biomass, and this is a flame. You can observe the producer gas. Okay, this is the, so the screw feeder played an important role in feeding of biomass. It works also like the one-way valve which restricts the black flow of the biomass feed. The good quality of producer gas is obtained. Now we have to go for the analysis, thermal analysis, then hydrodynamic analysis, and onwards. So, but the first phase, that is important phase, that production of the producer gas we had completed, and this is the major success in the PhD of Professor Tushar Patil. So with this, I am very much thankful to all, and one important thing I want to specially mention here. I have to mention, because you observe this. I had shown this figure to you. So this was the experiment I was performing in energy lab, and this was successful at 1:30 p.m. At 1:30 p.m. So I was carrying the experiment. Carrying the experiment, but I didn't come to know that what was the time. And when it was successful, at the same time, I called to my supervisor, who is a very, very generous person, Professor Pinakeshwar Mahanta sir, who is presently director of the NIT. At 1:30 p.m., he pick up my phone. And congratulate me. And he was ready, but I stopped, sir. We performed the same experiment on the second day. I will show you all the things. Then I had shown him. But that was the spirit, that was the motivation that I received from my guide. So here I am very, very much thankful to my supervisor, Professor Pinakeshwar Mahanta, and giving the opportunity, my PhD mate, my good friend, Professor Manjula Madam. I am very much thankful. Now it is open for the questions. Thank you very much.
Thank you, Shilke sir. It was exhaustive research work that you have shown us. I am really happy that you are continuing your work, and with such a successfully you have done it. Thank you so much for showing interest for this session. Otherwise, we would have missed it. Anyway, students, if you have any question regarding this, you can ask. You have one-time opportunity you are getting now, so you must grab it. Ask anything you want to.
Yes, please. I think they understood it in good fashion.
It is quite possible, sir, because you have explained everything in such beautiful manner. Like the language is so simple, but of course the experiment was quite complicated, difficult. But you have explained it in a simple manner that even like I could. I feel that I was observing the experiment that you were performing. It was something like that. You have explained it. Thank you so much, sir. And
Thank
thank you
you.
so much for joining us. And when we'll do this kind of program once again, definitely we'll one lecture will be definitely reserved for you, sir.
Thank you,
Your
madam.
book for next session also, sir. Thank you so much.
Thank you very much. Thank you to the participants also. They listen me very peacefully, quite.
Yeah,
And you
and
can ask
definitely
me
they have
questions
plenty.
in the chat box.
Hmm.
I will personally, or you can contact me. I will put my mail ID and all that with the madam. You can ask me the questions. You can contact me. In gasification, with the grace of my supervisor, I am able to guide on the gasification experimentation. Thank you very much. Thank you, madam.
Sir, I want to introduce you with one of great personality, that is Vasant Farve sir.
Yeah.
Farve sir, namaste.
Sir is there.
Sir is there. Yeah, he is
I am
also from
happy to hear
Nasik.
his feedback. I will be happy to.
He is also from Nasik, Maharashtra, and he is one very important part of NIT Arunachal Pradesh. This year also he has graced our one program, that is like he took some classes for first year for engineering mechanics, and he is very much passionate about engineering mechanics, and his way of teaching is sometime if possible I'll make you attend his class. You'll
Yeah.
love it.
I know him personally. He's my first mentor basically. So
You know him?
yeah.
Oh, that's
He
that's
was my
really
first
cool.
principal. And he is
Really
very knowledgeable person. So
very
I request
knowledgeable.
the participant don't miss his lecture.
Mm.
Very excellent lecture you will get. Very good information you will get from his lecture.
Yeah. We are privileged to have him, and this time we couldn't do the program offline. Sir had to take online classes, but next time, when this COVID situation will be over, we'll definitely have you all people offline in NIT campus, and definitely we'll have a good time.
Thank you very much.
Thank you, Vasant sir, for joining us. Thank you, Shilka sir.
Thank you, ma'am.
And thank you, participants. So tomorrow at 10 o'clock, we'll have our session will start. Please do join. Thank you so much. And everybody, please fill up the attendance form and the feedback form for today. And please do it positively. Thank you so much. Thank you, sir.